Hi, in this video we're going to continue talking about the first derivative test and finding local extrema. So here it says find any relative extrema. So that is the same thing as asking for the local max or local min. So when you see extrema, that's essentially plural for local max and min, and also essentially means the peaks and valleys of a graph. And so in order to do that, we need to find our critical numbers. Critical numbers are where the derivative is 0 or undefined. And so in order to do that, let's find the derivative. So we're going to take the derivative. And here, this is a nice polynomial, so we're just going to take the general power rule. So I'm going to have 4x cubed minus 12x squared. So that's our derivative, and we want to set that equal to 0 and solve for x. And so what can we take out over here? So take out a 4x squared, and we're left with x minus 3 equal to 0. And now we can solve for x. So either 4x squared equals 0 or x minus 3 is 0. And so this is where we're going to get our critical numbers. So either x is 0 or x is equal to 3. And now we're going to be able to use the first derivative test in figuring out where the function is increasing or decreasing to be able to identify our peaks and valleys, local max, local min. Now remember that the first derivative test essentially says that if the derivative is positive, then the function is increasing. So let me write that out. And so then we're going to have a local max occurs when you have increasing to decreasing. So that's what gives you a local max. So you want to see that in your number line. And then the local min is the reverse of that. You go from decreasing to increasing. So let's look at the number line. So we're going to put our critical numbers here. So 0 and 3. And we're going to, so two critical numbers breaks up the number line into 3 different regions to test. And so we're going to test the derivative and see what the function is doing. So let's pick some test points. So from negative infinity to 0. So in the past, in previous videos, I did the table. Now I'm just going to pick the values, the test points, just to go a little bit faster. So between minus infinity and 0, I'm going to pick negative 1 and then plug it into the first derivative to see what it is. So when you plug in negative 1 into the first derivative, which is over here, 4x squared times x minus 3, so we'll say 4x squared times x minus 3. So when you plug in negative 1, so f prime of negative 1, what are you going to have? So we're looking for the sign of the derivative. Is it going to be positive or negative? So here you're going to have negative 1 squared times minus 1 minus 3. So anything square here is going to be positive. So I'm going to have a positive times a negative, which gives me negative. So the first derivative is negative, which means that the function is doing what? Increasing or decreasing. Derivative is negative, that means the function is decreasing. Now let's pick another test point, something between 0 and 3. So let's say x equals 2. You could pick 1 also. So f prime of 2, and again, we don't necessarily care too much about the value, but the sign. So the sign is what tells us. If it's positive, the function is increasing. If it's negative, the function is decreasing. So when I plug in 2 in here, 4 times 2 squared, that's going to be positive. And 2 minus 3 is negative. So positive times a negative is negative. So my derivative here continues to be negative. So the function is going to continue to decrease. So it's interesting. What is going on here at 0? Now notice that both of these, the derivative is 0. And let's see. So let's pick another test point between 3 and infinity. Let's say x equals 4. So f prime of 4 is going to be, this is always positive, so positive, and then 4 minus 3 is now positive. So positive times positive is positive. So derivative is positive, which tells me that the function is increasing. So what is going on here? I'm going to have a nothing changes here. Now the derivative is 0 there, but there's neither not a local max nor a local min. So this is what we call a saddle. And then at 3 you go from decreasing to increasing, so you're going to have a valley. So this is a local min. The local min occurs at x equals 3. To find it, plug it into the original function and you will get the y value for that local min. Another way to kind of look at this, as we move on from this section, we're going to want to graph these functions without using a graphing calculator. So notice that this function f of x is x to the 4th minus 4x cubed. I can take out an x cubed and I'm left with x minus 4, right? So that means that I have x-intercepts where? So I have an x-intercept at x equals 0 and at x equals 4. So that's where the function crosses the x-axis. Now, one of the things that is really helpful in order to graphing these functions is kind of remembering our knowledge from pre-calculus. Depending when you took pre-calculus, you might remember this, you might not. As we cross an x-intercept, we're going to behave, so the function is going to behave like the term that gives you that x-intercept. So for example, here at x equals 0, the term that gives me x equals 0 is the x to the 3rd. So that means that as I cross 0, I'm going to look like x cubed, which makes sense now looking at this as to why we have a saddle there. So this function is decreasing. So if I was going to do a rough sketch just based on my x-intercepts and my increasing versus decreasing, so let me bring in a grid. Alright, so here's my grid. So 0 is an x-intercept of the function, and also 4 is an x-intercept. And so as I was saying up here, right, the x-intercept at x equals 0 came from the x cubed term. So that means as we cross x equals 0, we're going to look like the function, we're going to behave the same way that x cubed behaves. But looking at this, I know that my function is decreasing from minus infinity to 0, crosses 0, and then it continues to decrease. So what that tells me then is, since I know that this is going to behave like the x cubed, but is decreasing, is going to have a saddle right there, behaving like the x cubed function. Bear with me as I try to do this freehand. So it's decreasing, we cross 0, and so that's what I mean, but it kind of does the cubic thing, and then it's going to continue to decrease, and then at some point, right, at where did we reach our minimum? Local min is at 3, and then it goes back up. And the reason it goes back up is because you're here decreasing, but then it has to come back and cross that x-intercept. And where did 4 come from? So x equals 4, that x-intercept came from the term x minus 4, which is a linear term. So this, as we cross x, as we cross 4, we're going to look like a line because this is a linear term. So for example, had this been square, we would have gotten to 4 and then do a parabola. We would have looked like a parabola there. So here it has to come somehow back up and then cross at 4. Let me fix that real quick. So not a very smooth graph just because I'm not all that proficient with my tablet in terms of graphing, but so the idea though here is that you're kind of looking like the x cubed function, and then we hit our local min at 3. So not drawn to scale here. Actually, I'll bring in the Desmos graph so you can see what I mean. Okay, so here we go. So this is a graph, not too bad. It's just that I need to get better at my tablet drawing. Anyway, but this is the graph of our function. So notice that we can see, so this is what I mean by about the saddle. So because our x-intercept is x equals 0, which came from the term x cubed, it does the same saddle as the x cubed function does, except that here, because we found that the function is decreasing, is going to do the saddle essentially in reverse. And then we have our local min it occurs at x equals 3. That's where our local min happens. So here at 3, that's where the local min occurs, and this is our local min. So how do you find it? We will say this is the local min 3 f of 3. So you have to find the value of f of 3. Now remember, our function was x to the 4th minus 4x cubed. So when you plug in 3 in here, that's going to give you the y value of the local min, right? But so this is our function. So you have a saddle there and you have a local min. There's our x-intercept of 4, and so we cross it like a line. And so it's things like this are helpful when we're graphing functions. And in the next part of this section is we're going to learn about what the second derivative tells us about the graph. So notice that just from knowing the x-intercepts and knowing how the graph moves, increasing or decreasing, and finding its local max, mins, or saddles, I can pretty much get an idea, right? This is my rough idea of what the graph looked like with the limited information that I know. The next part of this is going to be the second derivative. The second derivative is going to give us the curvature of the graph. So like in this case, right, it's curving upwards and then it switches to curving downward and then it curves up again. And so the second derivative gives us curvature. So as we learn more about that, we're going to be able to put together a graph. So the reason that I didn't give you the Desmos right away is because our goal is going to be able to, based on the information that we're finding from the derivatives, is we're going to try to put together the graph without a graphing calculator or without technology, which is why for my class I'm saying in this semester, right, in this Calc 1, no graphing calculators, mainly because of this section. We want to be able to graph these functions based on the information we're obtaining from the derivatives rather than relying on technology. But just really quickly to go back to the intercepts. So for example, if I said something like the function was x cubed times x minus 2 squared times x plus 1, what will the graph look like? Right, I will have to know a lot more about this function, but just based on this, I know that we have x-intercepts at 0, right, the x cubed, at x equals 2, and at x equals -1. And so from pre-calculus, I know that based on the power of the term, that tells me how I cross that intercept. So when we cross x equals 0, 0 came from the term x cubed, so we're going to look like the cubic function as we cross it. When we cross x equals 2, this came from the x minus 2 squared term, so then that means that we're going to look like a parabola when we cross it. And then x equals -1 came from the term x plus 1, which is to the first power, so we're going to look like a line when we cross it. And so just with that information, I already know a lot about the graph. So then from the first derivative, what I'm going to need is knowing how am I approaching these, right? Am I decreasing as I approach -1? So if I was going to put this in my grid, it will be -1, 0, and 2. So as I come to -1, am I decreasing as I come to it, or am I increasing as I come to it? So that's going to come from the first derivative. So say for example, that I was increasing as I come to it. So then I'm gonna cross it like a line, right? But then I have to come back here and cross 0. And when I cross 0, I need to look like a cubic. So it's gonna have that saddle. And then as I cross 2, we're gonna look like a parabola. So that means I'm from that saddle coming back. I have to then somehow come back and create a parabola there. So something like this. So you gotta have that at x equals -1, you have to go through it like a line does. At 0, when we go through 0, we have to look like the saddle, like the cubic does. And when we hit 2, we have to be like a parabola as we hit it. So knowing the degree of the term that our x-intercept is coming from already tells us a lot about the graph. Then the first derivative is going to come in and tell us, well, which way, right? If I'm increasing, then this is what my graph looks like. If I'm decreasing, then it's going to be the flip of that graph. And then the second derivative is going to come in and tell us how are we curving. Okay, so that's a little preview of coming attractions. So as we go through the rest of this section, our next topic is exploring what does the second derivative tell us and how do we find all the information and then putting it all together by graphing. All right, contact me if you have any questions.